I decided to go ahead and add one more thing to problem number 85. I think you could probably figure this out, but just in case there's a little bit of confusion, I want to clear this up. Notice that at the end of the motion, the transverse velocity was 6 inches per second. Now I know that's off the screen a bit, but if you just watched the solution for 85, you know that was 6 inches per second. Now here's what's interesting about this problem. I answered the question after the ball had come to rest against the stop at B. Now it has to be this way, that the tangential velocity has to be 6 inches per second, and the reason it has to be that way is because the momentum has to be conserved. The angular momentum has to be conserved in this problem. But the question might arise, what is the velocity of the ball just before impact? How does that work? Well, here's the way to think about it. Hopefully you'll remember the 6 inches per second. You'll remember the, well, let's leave that up. But the key to this is that there is no acceleration whatsoever. We've already shown that. Throughout the entire motion, there can be no acceleration because it really doesn't matter what position you look at or where the ball is located along OB, there are no forces. So there can be no acceleration. And what that means is, let's say that we start with the arm OB horizontal, and I guess I'll go ahead and get rid of this free body diagram and the angular speed. Oh, let me jot it down. The angular speed omega 1 was 8 radians per second. Anyway, if I draw the arm, O here, B out here, we know that's 12 inches. The ball A begins at 3 inches from O. Now here's what's interesting about this. If there are no forces, then the ball cannot speed up or slow down. The ball has to go at 24 inches per second. That's what it began at. So it will continue moving in this direction at a constant velocity of 24 inches per second until it reaches the stop. Now how will it reach the stop? Well, remember, arm OB is rotating, right? It's moving up. So eventually OB will have to come up something like this. And the ball will just continue until it meets the stop at B. Now I'm going to get rid of some more of this so that we can have a little bit of space for our discussion. Now at the instant before the ball hits the stop at B, it is still moving at, let me make this larger in fact, and I think I'm going to switch colors here. The ball is still moving at 24 inches per second. Why? Because it has had no forces whatsoever applied to it. So fortunately I got lucky and the velocity I needed ended up right here. So this is the velocity even after the arm has rotated. Now be careful here. You might be tempted to think that the rotational speed is constant. It is not. The rotational speed is whatever is needed to simply follow the ball so that the ball moves at constant speed, 24 inches per second, until it reaches this point. Remember, the key to this problem is that the arm is massless, so it takes no force to accelerate or decelerate it. In any case, now is that realistic? Well, of course there's nothing that's massless as far as I know, but it could be small by comparison to the ball, so it would be a small effect and this would be a reasonable estimate. In any case, we already know that once the ball reaches B and stops, the angular momentum would be conserved, right? And so, well, I'm thinking twice about that now, because after it reaches B, B is going to apply a force, so we'll have to think about that a little more. But anyway, once A reaches B just before impact, then we know that the velocity of the ball in the transverse direction would be 6 inches per second. We knew that by conservation of angular momentum. No, we still know that, because even B is just going to apply a central force. So I stand corrected. I'm sorry, I'm getting myself all confused here. But yeah, the angular momentum has to be conserved even with a central seeking force. There's still no transverse force. And so even after the ball has reached B and hit B, then the speed, pardon me, the transverse speed is still 6 inches per second. Now just before impact it was 24 inches per second. And so what that means is that there must have been excuse me, there must have been a component of this velocity in the transverse direction to the arm that was 6 inches per second when this was 24 inches per second. Now, it shouldn't surprise you to think about this because the angle here, if we're interested in the angle at which this happens, let's see, we've got a 12-inch side here because O to B is 12 inches. We've got a 3-inch side over here, so we just have a right triangle essentially. And then if you think about it, there's a 90-degree angle here, and so let's see, the angle here which is opposite this angle would be this angle here, and this angle would have to be the same angle as the one down here. So basically, we know that the sum of the interior angles is 180, so get rid of the 90 degrees here. These two have to sum to 90, right? And so these two have to sum to 90 as well. Therefore, this angle is equal to this angle. Now, if you go through the geometry and calculate the length of this side, you take the square root of 12 squared less 3 squared by Pythagoras there, and you get 11 point some odd, I've got it on my calculation sheet here, 11.62 or so inches. Okay, so that's the length of this side. Now, if you look at the numbers, this side that's 6 is like this side that's 3. This side that's 12 is the hypotenuse, whereas this side that's 24 is the hypotenuse. Notice the numbers here are just double these numbers. So that means that the velocity before impact in the radial direction would be 11.62 times 2. So 20, what do we have? 23 point, let's see, 122.24 or so. Right? And that's, of course, inches per second. Because these are just similar triangles. The geometry triangle is similar to the velocity triangle. And so just before impact, the ball was moving out in the radial direction at 23.24 inches per second and in the transverse direction at 6 inches per second for a vector total, or a vector sum, of 24 inches per second. Because it's had no forces applied to it. And then when the stop at B applied a force, whatever force was required to completely eliminate the radial motion, then the ball had to maintain 6 inches per second because of conservation of angular momentum. And so that answers the question that I posed at the end of the solution for problem 85.